Recently, we introduced the concept of making aqueous solutions by dissolving various types of solid compounds in water. Before diving further into reactions that take place in solution, there are a few more general concepts about the dissolution process that we should touch on. First, even though we've seen the dissolution process diagrammed out a few times now, we've mostly talked about what will happen in principle when a small amount of solute interacts with a large amount of solvent. This picture is a little incomplete, because we probably know from experience that the amount of material you're trying to dissolve in your solvent matters for what's actually going to happen. Anyone who's ever done any baking knows that if you attempt to dissolve 2 cups of sugar in half a cup of water, it's probably not going to go too well. But if you add 3 cups of water instead, you'll get all those sugar crystals dissolved almost completely without too much effort. This example illustrates the property of solubility, which is a quantity that tells you the maximum amount of your solute that can be dissolved in a given amount of solvent. In that first example, the amount of sugar we were trying to dissolve exceeded the listed solubility for sucrose. So what happened was that no more sugar dissolved after that maximum amount was reached. Maxing out the capacity of your solvent like this creates what we would call a saturated solution, one that can't accommodate any more dissolved solute. Every material has some solubility value for every solvent, even if it's vanishingly small. We have different adjectives that would describe the solute in each of these cases, ranging from very or freely soluble for large solubility values, down to just insoluble at the low extreme. But it's important in our future discussions to remember that key point here, which is that solubility exists on a spectrum. Let's look at this a little more closely. Solubility is a complex property, and it turns out that the conditions you use when dissolving something can actually affect the solubility of your material. We've been talking about solids dissolving in water for a while, but let's take a break from that for a minute and consider a gas dissolving in water instead. It's a similar picture, except that there aren't any significant IMFs to overcome between gas molecules. But of course, that means that there's also less for the water to gain by interacting with the gas particles, so the solubility of most gases in water is relatively low compared to some other dissolution examples we've seen. Imagine, though, what might happen if you increase the gas pressure. The gas particles will be more crowded, and they'll interact with the water molecules more often, right? Ultimately, more gas is going to end up dissolved at this higher pressure, so we'd say that our gas solubility increased. For many gases, the relationship between pressure and solubility is a direct proportionality, and we actually have a simple equation called Henry's law that relates them together. The constant here is empirically determined for every gas, and varies based on familiar considerations like the size and polarity of the gas particles. Incidentally, Henry's law is the reason that we have carbonated beverages. These drinks are sealed under high pressure with gaseous CO2 at the factory, so lots more CO2 ends up dissolved than we would see under ambient conditions. When you open a can or bottle that's in this state, the extra pressure is released, and you end up with bubbles of CO2 that gradually make their way back out of the liquid. Carbonated drinks under ambient pressure are an example of supersaturated solutions, where the amount of dissolved solute exceeds its solubility under current conditions. There are all sorts of other fun applications of this concept, like the chemistry inside chemical hand warmers and the formation of rock candy, which you might want to check out on your own. It's also definitely worth noting that pressure isn't the only factor that can affect solubility. Temperature is another major influencer, for example. In general, most solids show increased aqueous solubility with increasing temperature, and most gases show decreased solubility under the same trend. These relationships aren't completely universal or constant, though, and we can see some exceptions on our charts here. For now, that's where we'll leave this discussion. The nuances of solubility will be discussed much more thoroughly later on, but it's good to have this overview in mind before looking at reactions involving dissolved compounds. Thanks for watching.